Hi everyone, this is your struggling CS student, and today let's solve another LeetCode problem of the day. Let's take a look at today's problem, 3542, minimum operations to convert all elements to zero. Okay, it's a 1900 question, give or take, so it's going to be quite challenging, I would imagine. So you're given an array nums of size n consisting of non-negative integers. Okay, the task is to apply some possibly zero operations on the array so that all elements have become zero. So in one operation, you can select a subarray from I to j inclusive, where I and j is between the bounds of the array, and set all occurrence of the minimum non-negative integer in that subarray to zero. And you can set all occurrence of the minimum, return the minimum number of operations required to make all elements in the array zero. So for example, here, you can select the subarray 1, 1, which is 2, where the minimum non-negative integer is 2, and set all occurrences of 2 to 0. Thus, the minimum number of operations required is 1. Here, you can select the subarray from 1 to 3 inclusive. Okay, 0, 1, 2, 3, which is 1 to 1, where the minimum non-negative integer is 1. Setting all occurrences of 1 to 0 results in this. Then you can apply this and this. 1, 2, 3. Selecting a subarray, which is the whole array, where the minimum non-negative integer is 1, setting all occurrences of 1 to 0 results in this. Then you can apply the operation one at a time. Oh, I see. Let me see this. So you set this to 0, 0, then you can only operate on this. I see. Kind of interesting, I guess. So like let's take a look at the constraints. N is 10 to the power 5, so the algorithm has to be n log n or better in terms of the time complexity. Space complexity, same thing, n or n log n cannot be n squared for both the time and the space complexity. So one interesting observation, I guess, that I can make is that once you have like the zeros form like a wall between the elements, such that you can never go your array shouldn't, like, for any operation that you're doing, your operation, the subarray that you're selecting shouldn't involve zero, because once you select, like, if your subarray involves zero, then the minimum non-negative integer in that case would be zero, and then you can set all occurrences of zero to zero, right? And in that case, it's considered you might as well not select that array that involves zero. So like another observation that I was thinking of is like, oh, why don't we just do greedy, right? We just do greedy and select the we want to make as many numbers zero. Uh, we want to make as many numbers in the array to zero if we can, in one operation. That will minimize the number of operations that we need to perform. So in this case, because the frequencies of or rather the lowest element is 1 in this case. So yeah, you might as well just select the subarray. Like, it wouldn't have made a difference in this case. I'm not sure if greedy works. I don't. There's no. There's no. There's no insight that I can make that can allow us to make like the greedy move. The greedy move would be something like you select the smallest number every time and you try to apply the operation one at a time, something like that. You select the operation that will give you the most number of zeros. Actually, wouldn't you just select the whole subarray all the time? Yeah, you can just select the whole subarray. Or is there like an optimal number of moves? What are the cases? That was my previous thumbnail. What are the cases? I mean, you definitely can do some sort of like, you can definitely guess the answer, but the question becomes how do you implement the check function? What I mean by guess the answer is that you can always do binary search on the number of operations. In this case, the minimum number of operations would be 0, and the maximum number of operations would be the size of the input, or n in this case. Because you can always change like one subarray of length 1 to 0, right? So that will take like n operations. You can just do, each element one at a time. Or you can do 0 number of operations, and then you try to guess, well, like what would the check function be? I don't know. Maybe you just do greedy. It's up to 10 to the power of 5. So my guess would be it's most likely greedy. Yeah, but it's just a guess though. uh, okay, let's think about this. Let's say we use alphabets, right? Let's say we use alphabet as an example. So suppose we have like A, which is less than B, A, B, C, and A, C, B, or whatever. Then you have like zeros, and then you have like A, B, C. Okay. So in this case, you know, this forms a wall, right? Like you would never select a subarray that involves these two elements. Because if you do this, then the minimum non-negative number becomes 0, then it is like a wasted operation. Okay, that much we know for sure. So in any subarray that you are choosing, it shouldn't include the 0. So you can almost treat it as like two different subarrays, two different arrays. Okay. So consider this subarray, right? Let's see. Like how would we do this? Maybe we do this one first. So we set this to 0, then we set this to 0. In that case, in that case, you create another partition here and here. Now you have like 3 partitions, and we've already done one operation. So in this case, we can only do 2 operations. We can do 2 operations here, and then we do 3 operations here. So it's like 1, 2, 3, 4, 5, 6, 7, 8 operations. 8 being the one with the original operation. Is that the answer? Even so, the implementation will be tricky, even if, let us say, that is the algorithm, right? You have 1, 2, 3, 1, 3, 2, then you have 0, 0, and then you have 1, 2, 3 again. 1, 2, 3. Okay. Is the answer 8? Yeah, the answer is 8. Okay. That doesn't really help me though. So if I guess, it's like 1, 2, 3, 4, 5. It takes 5 moves. Okay, so you can only save a move, possibly. Okay, you can save a move if there are like 2 elements that are the same. If all the elements are different, in this case, then there's no moves to be saved. And let me see, for this case, actually, are there any moves that are saved? 1, 2, 3, 4, 5, 6, 7, 8, 9. So actually there is a move that is being saved. Because we managed to remove these two in one operations, as in we managed to get these two ones to 0. So like it's better than just uh selecting each element a subarray of length 1 and then setting it to 0. So in this case it did better than 9 moves. Minimum number of operations to cover R elements is 0. I think you can definitely like group the elements together and then you try to solve them like one group at a time. So you group all the non-zero elements together and you group all the 0 elements together. So the 0 elements together you don't do anything. But for all the elements that are grouped together here, what's the answer here? The answer would be 1, 2, 3, 4, 5. Okay, so it's 0, B, C, 0, C, B. Actually, you don't really have a choice. You don't really have a choice, right? Because let's say at this point, you have A, B, C, A, C, B, right? Like greedily, you just select this, right? For each particular sequence of non-zero elements, you just select you just select the so if let's say there was another A here, you would just select you can only select the minimum element and make them 0. Is that really the case? Suppose, it's A, B, 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 then you have like A, maybe make it a little bit more exaggerated. In this case, the answer would be, yeah, you wouldn't do this first, no matter what, right? Because if you set this to 0, okay, then you create a wall here. So you need 1 operation, 2 operation, and then 3 operations. Whereas if you select the minimum element in the first place, that's 1 operation, and that's 2 operations. Okay. What if it's like this? The minimum element also forms like a wall. So you always want to process the minimum element first, I think. Because, okay, let's say we don't process the minimum element first. So this becomes 0, this becomes 0, that's 2 operations. 1, 2, 3, that's 5 operations. While we process the minimum element first, we can select a subarray of the entire array. That's 1 operation. That's 2 operations and 3 operations. So that's better than the 5 that we had previously. Okay, okay. What if it's like this? You have another A here, then you have another B, another C. So you still clear this out in one operation, and then you have to clear this no matter what individually. But the implementation seems a little bit tricky, even if that is the case. Even if that is the case, because you have to keep track of the positions, right? You have to like say, okay, for A, you're mapped to like 0, 1, 2, 3, and 4, and then B, you're mapped to 0, 1, 2, 3, 4, 5. And for C, you're mapped to 0, 1, 2, 3, 4, 5, 6, 2, and 6. So you say, okay, we process this first. Process this first. That means, well, what does this mean? We need to keep track of the walls. How do we keep track of the walls? 0, 3, 4. Okay, we cannot cross the walls. We cannot cross the walls. So now you say like your walls is like 0, 3, 4. Then you want to select a range. This is the next smallest number. You want to select a range in this number that doesn't cross a wall. So you say selecting one element is always fine, but if you want to select 1 to 5, so it's like you have 0, 1, 2, 3. You have this segment here, and then you have another segment here. So you're selecting 1. It's hard. It's hard. You're selecting 1, but you can't go 5. How do you keep track of stuff like that? Hmm. Okay, let's take a step back. Let's take a step back. Let's say A, just the same example. A, B, C, A, B, C. A, A, B, and C. Let's just mark the points between the same elements. So you have like 1, this, and you have B like this, and then you have C like this. How does this help me? uh, hmm. The constraints are very, very strict. Okay, I'm stuck. We have to somehow keep track of the walls. That I'm sure. So you do this, then you want, okay, so it's like, imagine initially your walls are here. So you have like a wall here, and you like have a wall here, right? So you'll say your wall is like, do we have to use a sorted list, really? Okay, initially you will say your wall is like negative infinity or something, right? Then you say you update your walls to be here, and no, it's not good enough. You have to keep track of like the middle wall as well. Okay, let's say we have to keep track. Let's say we use a sorted list, and we keep track of the walls, right? Keep track of the walls. That means you have like your walls will be at 0, 3, and 4. Okay, then you go through the next element B here, and then you say, you know, uh, your subarray will always involve two elements, but you can always select one, right? Okay, so you say, I think we can consider two cases. I think we consider let's consider the good case first. The good case would be like, let's say B is here. If B is here, then for every pair of elements, right? For every pair of elements representing a range, right? Then we want to see how far we can extend that range. In this case, that is 1 and 2. Then we will check, you know, if the next greater element between like these two pairs of numbers are the same, in like which is 3 in this case. Uh, we can do that check in log n time if we use a sorted list or a tree map. So suppose that there are like more bees here. Yeah. Okay, let me update the example. Um, uh, so B, yeah, B have 0 here, and you have this 0, 1, 2, 3, 4, 5. Actually, let's make the example more complex. Let's say this is C. This is C. Okay, so the first element will form the initial wall, I guess. So then you have like 0, 1, 2, 3, 4, 5, and 6. Okay, this is sorted. This has to be sorted. Okay, so once that's done, we process the next smallest number. The next smallest number in this case would be B's. So you'll be keeping track of like 1 to 1, 2, 3, 4, 5, 6, 7. Okay, 7. Okay, then we say for we use like a left right pointer or whatever, right? We say okay, we check like this. Is are these two elements the next greater number, is it 5? Again, we can do this check in log n time because 0, 5, 6 is sorted. And we also have to do insertion and maintain the sorted property. And a sorted list allows us to do that. Okay. So because these two elements, we'll try to extend the range as much as we can. So once you have done that, then you'll check the next one, like 4. Then you say in this case 1 and 4, the next greater element is still 7 in this case. So that's good. That's good. So we try to extend the range again. Try to extend the range again. And then we say in this case, do they share the next greater element? The answer is no, because 7 is bigger than everything. And 1's next greater number would be 5, right? Then we say in this case there will be like 0, 1, 2, 3. We say like we process 3 numbers or something. So it would process 3 numbers. No, we'll create a new segment. We'll create a new segment. So as long as the check passes, we only do one. We need do at least one. We need at least one segment. If the check fails, we'll do a segment plus one. Segment plus one. That means that represents the operation where we delete this in one operation and this in another, and we deleted this in one operation as well. So let me just color mark the operations. So 0, 5, 6 is one operation, 1, 3, 4 is another operation, 7 is another operation, like so. Then we check I'm running out of colors. We check this one. Check C and 2 and 8. Well, we know that the next greater number is 3, so we need to increment the segment by 1. And then we know that 8 is actually the largest number, so we have to increment the segment by another 1. So this will be 8. So let's see. 1, 2, 3, 4, 5. So the answer for this is 5 operations. Okay. I think implementation is still a little bit tricky. So let's say 1. This is 1, 2, 3, 2, 2, 1, 1, 2, 3. One, 2, 3, 2, 2. What? 1. Okay. 1, 2, 3, 2, 2, 1, 1, 2, 3. 1, 2, 3, 2, 2, 1, 1, 2, 3. So the answer is 5, right? Yep. Okay. So I swear the problems that involve some sorted list is always like a bit of it's difficulty curve for me, I guess, because this is like LeetCode specific. You might not always you don't have like sorted lists available to you in like HackerRank or whatever online platform they allow you to use for interviews or online assessment. But this is like a weakness of Python, unfortunately. I believe it like in C++ or whatever, you have like the standard template library or whatever, and they have like the tree map equivalent. So the sorted list is kind of like a tree map or like a self-balancing tree map where you can maintain an insertion. Can maintain insertion into a sorted data structure in log in time, and you also can do that kind of like ranking operations, like you check what is the next greater element or something like that. Okay, so let's just do that. So we have like the number and the group in from either tools import group by, and group by nums, lambda, or the key is equals to lambda num, and num is equals to 0. Great. I guess we can put the num first, the group. If num is equals to 0, we can continue. Group equal this group, and then we can print it. Just to take a look at the output, turn 0 for now. So what the group by function do is that it groups a sequence of elements in an array that share the same key. So what we are saying is, if number is equals to 0, we want to group a sequence of elements together. If they're not, we also want to group them together. So what this means essentially, you will get like this as a group, this as another, and this as another group. Now, because in this case we're only printing so this is the key. This is the key that groups the sequence of elements together. Now note that it is a sequence of elements, so the order matters. So in this case, what we expect for test case 4 is this sequence here and this sequence here. And what is given to you is actually an iterator. So you actually have to consume the iterator like so in order to get the whole list available to you. So, oh, wait, what? Case 4, if num is equals to 0, continue. I guess it will be like this actually. Okay, fine. So if they don't share the zeros, then they are grouped together. If they share the zeros, well, they're not grouped together. Okay, so now we have these two sequence of elements. We can process them greedily. That's the strategy that I'm going for using a sorted list. I'm not sure if it's like entirely correct, but let's just roll with it. So we will have like a sorted list. Let's go to sorted list, and then we say we need to group the elements by their indices. So maybe like the index map, I guess. Index map, and then we also have to process the smallest number at a time. Okay. How should I do that? Okay, let's create the index map first. Okay. Index map is like so. And for num in for index num in enumerate the group, we will say index map the append index. Index, this has to be a default dig. So default dig is essentially from collections. Collections import default dig. Okay. Now we need to process the elements in a sorted order by the key, by the number. So how should I do this? It's a bit like ugly, I guess. Sorted group of keys for key in, and for index, I think we need to update the 2 pointers, right? So say L is equals to 0 for R in range. For R in range of length of group of key. we need to process it. Then we need to say this is segments. The segments needed. Segments is equals to 0. And so this is total segments. Total segments. Total segments is 0 will eventually return total segments. Okay, here we say bisect left. So here we need to import another thing here. So bisect import bisect left. Okay. So bisect left on the sorted list. Oh. And the sorted list actually has to be on top. So consume the group iterator. Then create index map here. Then we need the sorted list to keep track of the walls. Then this is the segments. Bisect left on the sorted list on the index itself, right? Index itself, which is L. So that's I is equals to this. And J is equals to bisect underscore left on the sorted list of R. So if there's a same, that's good. So if I is not equals to J, okay, if I is not equals to J, then your left is equals to R, then segments plus equals 1. And actually, initially, we always have one segment. Then we say total segments plus equals segments. Okay, let's take a look. Index map of the number. This object, oh, this is not a group. This is the index map dot keys. Oh, this is the index map. Okay, let's see what's wrong. 2 operations. Oh no. Print group. So we're definitely processing this group, but it thinks it only needs to do 1 operation. Now, why is that? It's almost as if this didn't do anything. Let me extend the right. This is L R I G. Well, let's check the key as well. Key. Maybe index map of key. Okay, let's see. So processing index 1, index 3, that's good. So left is 0 and 1. So left 0 and 1. And also we never update the sorted list. We need to update the sorted list. Okay, let's think about this. No, it's not L itself. It's index map of key of L. So 0, 0, yeah, that's what we expect. So initially that will only be 1 segment here. Okay, then we need to iterate through this. Can we build it as we go? Okay, let's not be let's not mature optimize it. After we process it, we actually have to add it to the list. Sorted list dot add this one. I guess. It's still one. Okay, okay. Why is that? Left? No, I don't see left. One, three. So it's one segment. Okay. Then we process two. Ah, shit. Okay. Now we need to update it here. Oh shit! Nice. Oh, okay. All the shit passes. But I was wondering, if we can add it here immediately. Like, I mean, add it in this loop. If it's possible to add it in this loop. Uh, I don't think we can. No, I don't think we can. Yeah. That's because it always depends. Like, yeah, we have to do it one step at a time. But let's try it. There's no harm trying. Oh, this would be R, I guess. Yeah. It seems good. It seems good. Let's just give it some random test and see if it passes or not. So if like, I don't know, uh, okay, seems good. So it is a greedy strategy which makes use of the sorted list. But okay, let's submit it first and make sure it's correct. All right, submit. Ooh, the runtime is. Wait, really? TLE, I can't believe this shit. Okay, let's use these test keys. Okay, basically it's a running sequence of numbers. Is my time complexity really n square? Is my time complexity really n square? Uh, oh, shit. Actually, we don't need this check, right? Okay, we need the check. Default list. We group a sequence of elements together. Okay, this is like O n time. Then we do another O n loop. but this is fine. We only check each element twice. This consumes it as well, so that's another ON operation. Then for each key, yeah, we're just processing each index at least once. Then we do a login check. Then process it just once again. It should be fine though. Yeah, there's only one group in that case. 10,000 operations. Okay, let's see the group. Index map block keys. It shouldn't take. Yeah, this this operation should be fine, right? Because we're only sorting on like a subset of the array. So if you combine all of them together, it should be like not n now. God dang it. Key and sorted index map dot keys. Is there a better way that I can do this? Uh, I guess we don't need this. Would that make it faster? uh, Not really. Okay, YOLO. Fuck, man. Fuck, I'm so close. So close. Okay, it made it a little bit better. Yeah, I'm stuck. Unfortunately, it is what it is. Uh, this isn't this all like isn't this like a reasonable amount of time? Oh man. 0, 1, 2, 3, 4, right? Yeah. Okay. So it's like 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. This took 5 operations. Can I do it any faster? 1, 1, 2, 3, 4, 5. Yeah, that's 5 operations. Is this the bottleneck? Hmm? Huh? Oh, I give myself 10 minutes. If I can figure it out, we just look at the answer together. There's no way. It's just wrong. Never mind, it's correct. Maintaining a global list like this. But still too slow though. Maybe we don't need to group the elements together. Index map, sorted list, sorted segments, numeric nums. That's even slower, and it's wrong. Okay. Still wrong. And it's slow as well. Key. Okay, I give up. I give up. Let's take a look at the answer. It was a good try, I guess. Hash table, stack, monotonic stack. Okay. Monotonic stack. Hmm. Let's see. Through observation, we can establish the following rules. Setting several identical minimum values to 0 simultaneously, yes. If smaller numbers exist between two identical numbers, those numbers cannot be turned to 0 together. Traverse the array while maintaining a monotonic increasing stack, which represents the current increasing sequence of non-zero elements. Okay. Now for each element A, if the top of the stack is greater than A, then according to rule 2, see. So for each element A, if the top of the stack is greater than 8, and according to rule 2, the top element cannot be operated together with subsequent elements, so it needs to be popped from the stack. A 0 is skipped since no operation is needed. Okay. If the stack is empty or the top element is less than, it means we need a new operation to cover A. So we push it on the stack. monotonic increasing. The top of the stack is greater than A. Smallest numbers exist between two identical numbers. These numbers are not smaller. Okay, let's assume that they are smaller. 4, 7. Huh? How can they be smaller? It's monotonically increasing, man. Okay, 8, 8, 4, 4, 8. The smallest number exists between two identical numbers. These numbers cannot be turned to 0 together. Yes, you need to turn this to 0 first, then this to this. Okay, so if the top of the stack is greater than A, top of the stack is greater than A, okay, so like, maybe we have like 1, 2, right? So it's 1, 2, 8, 4. The top of the stack is greater than A, then the it cannot be operated on by the subsequent elements. So in this case, you do 1, 2, 3, 4, 5. What? If A is 0, we skip it. Okay, if the stack is empty or the top element is less than A, it means we need a new operation to cover A. The top element is less than A. Okay, I have no idea, man. Yeah, I'll probably have to watch a video on this. But yeah, thanks for watching this video and I hope you have a great one.